Hello, everybody. Welcome to the lecture series on deep learning and its importance in biomedical data analysis. Before we understand the importance of deep learning in analyzing biomedical data, should need to get a grip on what is deep learning and how different it is from conventional machine learning models. What are the advantages of using deep learning model, and what are the different various or popular deep learning models that are being already deployed in the field of biomedical engineering or in the analysis of biomedical signals. Now, deep learning is nothing but an artificial intelligence based method that facilitates machines to understand and process like human brain. Just because they have the basic principle of how the brain works, they have the ability to recognize complex data patterns. For example, when you just lie down on a terrace and look at the sky filled with clouds, automatically your brain starts forming patterns, right? And you start identifying some as lions, some as tiger, some as mountains, or whatever. So, similar to that, these deep learning models, just because their working mechanism is very much closer to a working process of a brain, they have the ability to recognize complex data patterns present in the data given to them. Now, these deep structures in the deep learning models, they have interconnected nodes or neurons that mimic human brain. In human brain, whenever you see an object, it is not just eyes that sees an object. From the eye, the signals are taken into the occipital lobe. From there, it is being focused on to the working memory. And from the working memory, it identifies the object or the color or the place. And then you are made to realize what it is. So, whenever the brain works, it is not just one single lobe that is being put into work. It is always several lobes, interconnected neurons and nodes that are put into work. So these deep structures similarly have interconnected nodes that mimic human brain. Like any other machine learning algorithm or neural network, it has got one input layer and an output layer, in between several hidden layers. Now these several hidden layers, when it comes to deep learning, can be of any combination and can have any mathematical equation as a part of it. And these hidden layers can handle non-linear data sets very well. So, in a summary, deep learning models are nothing but an extension or a modification of the traditional machine learning models with an ability to look through the data for any intrinsic subtle patterns and handle large sets of nonlinear data. Now, why do we have to use deep learning for biomedical data? That's the next question we need to answer before we go into this question. It has got some inherent advantages. One is it has the ability to recognize complex patterns, as I already told you. The pattern need not be straightforward or explicit. It may not be visible to human eye or directly through any cases, but these deep learning models can recognize the intrinsic patterns which are hidden behind the signals. The second advantage is they can handle high dimensional data. When I say high dimensional data, it is of two folds. One, a single data from a single source of large quantum. For example, EEG data from 64 electrodes placed on the human head, recorded for a period of 8 hours, let's say, at a sampling rate of 512 hertz. So that means for every second there will be 512 sample points per electrode. Now imagine for 8 hours what's going to be the chunk of data. So it could be from one single source, a huge quantum of data, or smaller chunks of data from multiple sources. We call that as multimodal approach. So either way, these deep learning models are capable of handling high dimensional data. Sometimes we have even handled MRIs which are 4D in nature. And they have the ability to recognize complex pattern in diseases. Sometimes, especially in cancer identification, cancer detection, classification, or prediction, there are some tumors or lumps or which is recognized as white patches can hide behind extra muscle mass. And sometimes it could be even difficult for a clinician to identify them. In such cases, deep learning plays a better role in recognizing complex patterns and diseases. Now, since they have a capability to handle multidimensional or high dimensional data, uh, they have ability to handle multimodal data. They are very good in extracting features from large data sets. In the sense, uh, it doesn't need any human intervention. We don't have to go for handcrafted features. You just provide the data to the deep learning model. The deep learning model can study them, look into the patterns existing in a very exhaustive manner, and it will learn to extract features from large data sets by itself. While doing so, the deep learning will also reduce the dimensionality of the data, because more the data, more the computation. So deep learning has the ability to reduce the data as the data travels through the model. But at the same time, deep learning ensures that the important features which are responsible for or which contribute to the maximum performance of the model are retained without getting erased or thrown out. That is another very good or important advantage of deep learning, and the reason why it is being used in biomedical data. Now, I told you that these deep learning models are capable of extracting features from large data sets. So basically, automatically they extract the large data sets, eliminating the human intervention in extracting the features. Now, what is the problem in manual extraction of features? One of the biggest disadvantages, subjective analysis. For example, if I'm going to give you a sinusoid, probably amplitude may be one of the features according to you. Phase may be another feature according to me. Frequency may be another feature according to someone. So you will extract amplitude, feed it to the machine learning model. I will extract phase and feed it to the machine learning model. Somebody will extract frequency and feed it to the machine learning model. Somebody will convert it into frequency domain, extract the power in dB and feed it to the deep learning model. Now each of us have our own preferences. Sometimes what I pick may be successful. Sometimes what I pick may not be successful. In this context, it is very difficult to explain why the machine learning model failed to detect, predict, or classify. Okay, so this is the subjectiveness when it comes to manual feature extraction. Again, in order to ensure that my model will achieve 100% success, if I can do some magic and extract 10,000 features from a sinusoid, which will help us or which will make the machine learning model identify a sinusoid as sinusoid, thus that 10,000 feature set is a huge data set, and machine learning cannot handle such high data sets. So at some point, I am forced to reduce the 10,000 features into probably 1,000 features or 1,500 features. So when I do that, there is a high probability that I may miss out on real important features. Please remember one thing: whether it is handcrafted features or automatic extraction of features by deep learning, it is not necessary that significant features always contribute significantly for the classification or prediction or identification. Sometimes the significant features may contribute only 50% to the success of the model, whereas a very subtle small feature, even though it may be insignificant, could contribute like 70 to 80%. Okay, so when we do a manual feature extraction and reduction of features, it's highly probable that you may miss out on certain important data. Whereas when it comes to deep learning, since it is learning by itself and reducing the dimensionality by itself, it knows what's important, what needs to be retained, and what needs to be left out. So in that way, I'm not saying deep learning is the best, but it makes the probability of success better. And whenever there is a change in the pattern in the data, when you pass the data through the deep learning model during training, it adapts to the new data patterns that it can find in the raw data. Now, such a deep learning technique with so many advantages that fits the biomedical environment, what are the areas in which the deep learning is applied? One area is medical imaging, the other area is genomic analysis, and the other one is clinical data analysis. So these are the prime areas in which deep learning is deployed. Now, under medical imaging, deep learning can be used for disease detection, identification, classification, prediction, and it can also be used for image enhancement. So, when I say disease detection, a good example would be cancer identification in radiological images, or brain tumor segmentation in MRI scans, or diabetic retinopathy from the cornea or the eyes, or even sometimes minor scratches or tearing up of the cornea. So these are some of the examples of disease detection. And when it comes to image enhancement, majorly deep learning are used in noise reduction in medical images. So you get an MRI or a CT scan from the radiology department, it has to go to the doctor digitally. There could be noises associated with it. The major problem in radiological images getting corrupted with noises, it could result in false positives. That means a person may not have cancer, but because of the noise added, it could be, the image could look like as if the person has a cancer. So this is not good. Or a person may have cancer, and because of the noise, it could appear as if the person doesn't have a cancer. So it's very important that the medical images are noise free, and it's very important how you remove the noises. That plays a critical role. You removing the noise should not remove the features that are present, in detection of cancer. Or when you remove the noise, it shouldn't introduce more noise or features that will make the model identify no cancer as a cancer. So it's very important. Then resolution enhancement. Sometimes the clinicians has to zoom the images to have a closer look. Generally, once the resolution of an image is fixed, if you are going to zoom beyond the resolution, you are going to see pixelated images. So whereas deep learning models will aid in avoiding those pixelations, and AI models will help you have a better clarity when the pictures are zoomed in. So these are the areas in which deep learning is deployed in medical imaging as disease detection and image enhancement. And when it comes to genomic analysis, very interesting topic, high scope for research. They are involved in sequence analysis. DNA is a sequence of patterns. Okay, every one of us will have a DNA pattern. Okay, that's how they are able to identify just with a drop of saliva or a drop of blood. If they do a DNA analysis, they can match the DNA. It is highly used in forensics, or finding the issues regarding the parenting things. Now, uh, deep learning, since it is very good with pattern detection or identification of pattern, uh, genomic analysis is one good area where deep learning is greatly deployed. Again, in disease prediction, when it comes to disease prediction, uh, you won't believe, even before a kid or a child is born, with just a biopsy of mom's tissue and the fetal liquid in which the placenta in which the baby is in, they can do a gene sequencing and find out whether what are the types of diseases that this newborn babies will be prone to when they are born. A good example would be Down syndrome. Even before a baby is born, by doing a genome sequencing analysis and disease prediction, clinicians can come to me and say whether the newborn baby is going to suffer a Down syndrome with a probability or not. Such great applications are being done using deep learning in the area of genomic analysis. When it comes to clinical data analysis, patient monitoring. Patient monitoring is very, very important, and it has been automated in almost all the hospitals. Now, deep learning are taking care of the history of the patient's vitals before it makes a decision or decides to beep or raise an alarm. Similarly, treatment planning. What do you mean by treatment planning is the more customized the treatment planning is for a patient, the better the patient will recover. For example, I may have a headache, you may have a headache. The headache may be the same, the reason for the headache may also be the same. But my age is different, your age is different, my food habits is different, your food habits are different. So, my history of disease and medical conditions is different. Your history of disease and medical conditions are different. The tablets which I consume on a daily basis are different. The tablets that you consume in daily basis are different. So, a doctor cannot prescribe the same headache medicine for you and me. Okay, AI or deep learning helps the clinicians to have more customized treatment planning in clinical data analysis. Now, what are the most popular or key deep learning architectures that are used in the field of biomedical signal processing for data analytics? The first and the foremost is convolutional neural networks, shortly called as CNN. The second is recurrent neural networks called RNN. Then we have autoencoders and transformers. One by one, we'll see in detail what is their structure, what are the popular models in CNN, what is RNN, how is it different from CNN, what are the popular models adopted in under RNN, what is an autoencoder, what are transformers, how are they different from autoencoders, what are the different types of transformers that are there, attention mechanisms. We'll see a lot more in the future slides. Now, what is the advantage of using deep learning over traditional ML techniques? The first and the foremost is enhanced performance. The second one is automation, and third one is novel insights. When I say enhanced performance, what does it mean? It has got a very greater accuracy in diagnostics. Sometimes where clinicians fail to identify a pattern, deep learning does it for them. They have very good sensitivity and specificity. So what is sensitivity? What is specificity? If you are already introduced to the world of machine learning, you must be familiar with terms like false positives, false negatives, true negatives, true positives. These are the things that will help you to determine the accuracy or precision or F1 score of your model. If not, just please go Google, get the basics right. For example, true positive is identifying a cancer as a cancer. It's a true positive. Okay, a true negative is identifying a no cancer as a no cancer. That's true negative. What is false positive? Identifying a no cancer as a cancer is false positive. And false negative is identifying a no cancer, cancer as a no cancer. That's false negative. So, the false positive and the true negative has to be really, the true positive and true negative has to be really high. Only then the performance of the deep learning model will be very high. The true positive is nothing but the sensitivity, and true negative is nothing but the specificity. Deep learnings have an improved prediction capabilities. Okay, apart from detections and classification, they have very good prediction capabilities as well. Under the automation, I have already told you the reduced manual intervention either in terms of feature extraction or dimensionality reduction, which results in faster processing and making it scalable. Now, when I say novel insights, what do I mean? Again, I'm repeating, it's capable of identifying new hidden patterns and biomarkers to identify or classify or detect a particular disease. So if there is something consistently present across samples, deep learning has the ability to associate and then identify the hidden patterns. Now, is there only advantage of using a deep learning model? No. Every system will always have a pros and cons. Now, what are the challenges of using deep learning in biomedical data analysis? The challenges can be categorized into two: data related, technical. When it comes to data related, there are three main areas. One is data augmentation techniques, second one is limited data science, and the third one is data imbalance. Now, what is data augmentation? Generally, in image processing, the word augmentation refers to taking one particular image, varying its contrast, brightness, hue, saturation, rotating it by 90 degrees or 180 degrees, tilting it, stretching it, adding some white noise, adding some salt and pepper noise. So from one image, by doing all these things, you can generate another 100 images. This is what is called as augmentation. And generally, when deep learning are used for generic image processing based identification or classification, this augmentation is allowed and can be done in any way you want. But when it comes to biomedical imaging, it's very important that these data augmentation techniques are done carefully. Because as I said, when you augment, when you increase the brightness or a contrast, it could give a rise to new set of features which may make the model identify a particular image wrongly. Or just because you rotate it or you stretch it in a particular angle, a biomarker which is present for the identification could go hidden. So data augmentation cannot be done as such. It has to be done carefully with lot of restrictions. So that is one challenge. Second, limited data size. Deep learning models generally thrive on the data, quantum of data. The more data you give them, the more they can identify and the consistency in the pattern in the data, and the better they can perform. When the size becomes limited, data size becomes limited, still they can perform, but we need to do so many other aspects to take care of the limited data size. Generally, when it comes to biomedical data, one of the biggest problem is getting the quantum of data. You may have data sets available openly in public databases, but they may have only 12 samples or 13 samples or 30 samples when you need 100, 150, 200, 8,000, 10,000 of them. So that's a big challenge that we need to work around. The next most important is data imbalance. What is this data imbalance? For example, let's say we have gone to a hospital to collect the the CT scans of people who have lung cancer. So the hospital hands you over a pen drive with 5,000 images in there. Now, out of this 5,000 images which has been randomly taken from the patients, you will find 4,000 images with no cancer and only 1,000 images with cancer. So this is called data imbalance. Okay, the ratio is not the same. So why or how is it going to affect the deep model? When you train with the imbalanced data, generally the models has the ability to incline towards a data choice which has got more samples to learn from. For example, I give you two books. Okay, in one book everything is elaborated, explained clearly, lot of illustrations are given, and there is another book which has got very few illustrations and very few concepts listed or explained. Now, which book you go for? Obviously, you'll be biased towards the thicker one which has got all illustrations, all explanations. But remember, all illustrations, all explanations need not be correct. Even though the other book may be small, it could have everything right on it. Even though the other book may be really illustrations, but it may not have everything right on it. But as a model, generally you incline towards such books. Similarly, the deep learning models, when you have two classes and one of the class has more images for training than the other class, generally the model will lean towards the class which has got higher number of samples to learn. So this is called biasing based on the data imbalance. There are a lot of ways to counteract this data imbalance, which we will learn one by one in the forthcoming lectures. Then when it comes to technical, there are two major problems. One is called model interpretability. What is this model interpretability is when a doctor looks at a CT scan to identify a lung cancer or a pancreatic cancer or a colon cancer, he has certain biomarkers in his head based out of his experience, which he will look for in that image to identify those cancers. Now you give the same image to a deep learning model or an AI model, and it predicts the same, the cancer is there. Clinicians are afraid or have no idea of what these models are looking into to identify the cancer. Are these models looking at the same biomarkers what the clinicians is looking at, or is it a set of different biomarkers which the model is looking into to classify? Even though the endpoint is the same, yes cancer from both a doctor and a model, how the endpoint reached is matters. So clinicians generally don't trust deep learning model because they are a black box and exactly do not know what is happening inside them. But as a solution for that, now a new term has been coined called explainable AI, which not only gives you the result, but there is also a possibility to come out with an explanation of what these models are looking into to identify at their results. The next major problem is computation resources. I understand that when compared to a conventional machine learning model, convolution models, deep learning models, it doesn't give us the pain of extracting features from the signal. They automatically do that by themselves. That's the advantage. But on the downside, when a deep learning model has to be trained, it is very very difficult because the computational resource requirement is very high. When you want to extract features manually and then form a feature vector, train an SVM or an LDA or a decision tree or a regression, you can simply do it in a very normal PC with just CPU. It will work. But whereas if you want to train the same with a deep learning model, CPU will also work, but it's going to take, I don't know, probably 24 hours, 48 hours, 72 hours, or whatever it is, depending upon the complexity and the depth of the model. Whereas when you have a high performing system with a GPU, higher RAM, and everything, probably that number of hours may come down drastically. Just for an example to get a feel of it, Without GPU, if the algorithm runs to complete the training for about 24 hours, with GPU, probably it could finish in 1 hour. Just to give you a glimpse, it's not necessarily exactly the ratio is the same, but just telling you so to get a feel of it. So computational resource requirement is very high in deep learning, especially as the model grows deeper vertically or horizontally. So these are the challenges of using deep learning in biomedical data analysis. Having known all these facts, just to summarize, we saw what is deep learning, we saw why we want to use deep learning for biomedical data, what are the application areas in biomedical, what are the key deep learning architectures that are being used in biomedical data analysis, what are the advantages of using deep learning over ML techniques, and what are the challenges of using deep learning in biomedical data analysis. If you want, please go over this lecture any number of times. If you have any questions, you can always use ChatGPT or Google or Claude to get your questions clarified. Or if you have anything, you can WhatsApp me. I can answer you for that. In the next series of lectures, we will see what is a CNN, how does the structure look like, what are the important layers of the CNN, what are the different types of popular CNNs available, like UNet, what is a recurrent neural network, how is it constructed, what are the layers of RNN, what is LSTM, how is it related to RNN, what is an autoencoder, transformer. Thank you for your time.